Hello there, and welcome to this quiet corner of the cosmos, where wonder takes its time and the universe unfolds at the pace of dreams. Tonight we're not staying close to home. We're reaching far beyond the familiar boundaries of our solar system, beyond the comfortable orbits of planets we've known since childhood, into the vast emptiness between stars where something extraordinary has come calling. This is the story of Three-Eye Atlas, a visitor from depths of space so profound that its very existence challenges everything we thought we knew about size, about time, about the ancient choreography of objects drifting through the galactic dark. It's a name that might not mean much to you yet, but by the time we're done wandering through its implications together, you'll understand why astronomers around the world have been losing sleep over this singular, impossible thing. Before we begin to grasp what Three-Eye Atlas truly represents, we need to let go of our usual sense of scale. The measurements we use every day, the distances we walk, the sizes we can hold in our hands or even imagine with our eyes, all of that becomes useless when we try to comprehend what's currently racing through our solar system at speeds that make our fastest rockets look like they're standing still. If you're settling in for the night, letting your thoughts slow to match the rhythm of deep space itself, I'm glad you're here. Because what we're about to explore together isn't just about one object, however remarkable. It's about the realization that our solar system, our tiny corner of the galaxy, is not as isolated as we once believed. We live in a cosmic neighborhood where visitors arrive from unimaginable distances, carrying with them the secrets of star systems that died before our sun was even born. Tonight we'll take our time with this mystery. No rushing, no hurried explanations. Just a slow, careful examination of something so large and so ancient that it forces us to reconsider our place in a universe far stranger and more connected than we ever dared imagine. So find a comfortable position, let your breathing settle, and prepare to journey with me into scales of size and time that exist at the very edges of human comprehension. The first thing you need to understand about Three-Eye Atlas is that it shouldn't exist. Not in the way we typically think about things existing in our solar system anyway. When we look up at the night sky and consider the objects we share space with, the moon, the planets, the asteroids, we're looking at family. These are all pieces that form together from the same primordial disk of gas and dust that surrounded our young sun over 4.5 billion years ago. They're siblings, born from the same stellar nursery, shaped by the same gravitational forces, aged by the same solar wind. But Three-Eye Atlas is different. It's not family, it's a stranger that wandered in from the cold, carrying with it the chemical signature of an entirely different star system, an entirely different epoch of galactic history. When astronomers first spotted it on July 1st, 2025, using NASA's Atlas Survey telescope in Chile, they weren't just discovering another comet. They were making first contact with something that has been traveling through the void for longer than complex life has existed on Earth. To understand the scale of what we're dealing with, let's start with speed, because that's where the impossibility begins to reveal itself. Three-Eye Atlas is moving through our solar system at approximately 210,000 kilometers per hour. That's 130,000 miles per hour. To put that in perspective, if you could somehow board this cosmic wanderer, you could travel from New York to Los Angeles in less than 2 minutes. The space shuttle, at its fastest, reached speeds of about 79,500 miles per hour. Three-Eye Atlas is moving more than 7 times faster than that. But here's what makes that speed truly extraordinary. This isn't the speed of something that belongs here, something caught in the sun's gravitational embrace and following a predictable elliptical orbit. This is escape velocity and more. This is the speed of something that has broken free from the gravitational bonds of its home star system and spent eons accelerating through encounters with countless other stars, picking up momentum like a cosmic pinball until it achieved velocities that mark it as permanently, irrevocably free. The mathematics of its trajectory tell a story of wandering that spans geological ages. Its orbital eccentricity, the the measure of how elongated its path is, reaches 6.1. To understand what that means, consider that Earth's orbit has an eccentricity of 0.017, nearly circular. Even the most elliptical planetary orbits in our system rarely exceed 0.2, but 3I Atlas, with its eccentricity of 6.1, is following what's called a hyperbolic trajectory. It's not orbiting our Sun at all. It's simply passing through, like a bullet fired from some distant, unknowable place, destined to exit our solar system and continue its journey into the endless dark between stars. This trajectory tells us something profound about its origins. 3I Atlas has been approaching us from the direction of Sagittarius, from the general area where we look toward the center of our galaxy. It has been traveling for so long that by the time it reached us, the star system where it was born might not even exist anymore. Stars live and die on timescales that dwarf human civilization, and 3I Atlas has been wandering for so long that it might be carrying the only remaining evidence of stellar neighborhoods that were ancient when our sun was still forming. Now let's talk about size, because this is where 3I Atlas transforms from merely interesting to absolutely staggering. Determining the exact dimensions of something so far away and moving so fast presents challenges that push our observational technology to its limits. Different telescopes, using different methods and wavelengths of light, have provided estimates that range from conservative to mind-bending. The Hubble Space Telescope, our faithful eye in orbit, suggests that the nucleus of 3I Atlas, the solid core beneath its gaseous atmosphere, could be anywhere from 1,000 feet to 3.5 miles across. That lower estimate would make it roughly the size of a large skyscraper, comparable to the height of the Eiffel Tower. But even that conservative measurement represents billions of tons of ancient ice and rock that have survived a journey through interstellar space lasting millions or possibly billions of years. However, newer observations from the Vera C. Rubin Observatory paint a picture of something far more substantial. Their data suggests that 3I Atlas might be approximately 7 miles in diameter. 7 miles. To grasp what that means, imagine an object whose circumference could encompass the entire downtown area of a major city. Walk from one end to the other, and you'd be hiking for hours across terrain that formed in another star system, under another sun, in conditions we can only guess at. But even those measurements pale in comparison to the early estimates that sent shockwaves through the astronomical community. Some initial calculations suggested that 3I Atlas could be as wide as 12 miles, possibly even reaching diameters of 15 kilometers or more. While these numbers are likely overestimates that will be refined as we gather more data, they hint at the possibility that we're dealing with something of unprecedented scale among interstellar visitors. To understand why size matters so much in this context, we need to consider the previous interstellar objects that have graced us with their presence. In 2017, we discovered Oumuamua, the first confirmed visitor from beyond our solar system. Oumuamua was roughly 400 meters long, elongated like a cosmic cigar or perhaps a shard of some larger body. In 2019, we encountered 2I Borisov, another interstellar comet that measured less than a kilometer across. 3I Atlas dwarfs both of these previous visitors. Even at its most conservative estimated size, it's several times larger than Oumuamua. At its upper size estimates, it could be 50 to 100 times more massive. This scale difference isn't just academic. It represents exponentially more material, more ancient chemistry, more opportunities to study the composition and conditions of its distant birthplace. But the nucleus, the solid core, is only part of the story. Surrounding 3I Atlas is a coma, an atmosphere of gas and dust that extends far beyond the solid body at its center. Current observations show this coma spanning up to 26,400 by 24,700 kilometers. That's roughly twice the diameter of Earth. Imagine our entire planet, with all its continents and oceans, fitting comfortably inside the atmosphere of this wandering visitor. And even that isn't the full extent of its influence. NASA's SphereX mission detected an extended carbon dioxide coma, reaching at least 348,000 kilometers in radius. That's nearly the distance from Earth to the Moon. This invisible envelope of gas, detectable only in specific infrared wavelengths, creates a sphere of influence around 3I Atlas that could contain our entire Earth-Moon system with room to spare. These measurements force us to confront scales that exist at the intersection of the comprehensible and the cosmic. We can state the numbers, we can make the comparisons, but the reality of an object this size moving through space at such incredible velocity challenges our everyday intuitions about how the universe works. Consider the forces involved. This is not a small chunk of rock and ice drifting lazily through the void. This is a mountain-sized piece of an alien world, wrapped in an atmosphere larger than planets, racing through our solar system with enough momentum to reshape our understanding of what's possible in the spaces between stars. Every second, it's covering distances that would take a commercial airliner minutes to traverse, all while maintaining the structural integrity that has kept it intact through eons of cosmic bombardment and the harsh radiation of interstellar space. The implications ripple outward from these basic facts about size and speed. If objects this large can survive the journey between star systems, if they can maintain enough volatile materials to create extensive atmospheric envelopes, if they can traverse the galaxy while retaining the chemical signatures of their birthplaces, then the universe is far more connected than we ever imagined. The spaces between stars aren't empty barriers, they're highways, and traffic moves along them carrying news from distant neighborhoods of the galaxy. As 3I Atlas continues its passage through our solar system, approaching its closest point to the Sun in late October 2025, we're witnessing something that might not happen again for thousands or millions of years. A visitor this size, this well-preserved, this accessible to our instruments, represents a once-in-a-civilization opportunity to study the building blocks of worlds that formed under alien suns. The story is far from over. In the coming months, as 3I Atlas swings through the inner solar system, our most powerful telescopes will continue their careful observation, measuring, analysing, trying to decode the chemical messages it carries from its ancient home. But already, just from understanding its scale, we're forced to expand our conception of what the universe contains, what survives the journey between worlds, and what gifts the cosmic dark might deliver to our doorstep. The age of 3I Atlas opens doors to contemplations that stretch beyond the merely astronomical and into the philosophical. When we speak of something being 7 billion years old, we're not just discussing a number. We're touching the edge of a temporal abyss so profound that it makes human history appear as barely a whisper in the cosmic conversation. To understand what 7 billion years means, we need to step back and consider the timeline of everything we know. Our solar system formed roughly 4.6 billion years ago. Earth itself coalesced from cosmic dust and debris around that same time. The oldest rocks we've found on our planet date back about 4.4 billion years. Complex life, the kind that builds shells and leaves fossils, didn't appear until around 540 million years ago. Humans, in any form recognizable to us, have existed for perhaps 300,000 years. But 3I Atlas predates all of this. It was already ancient when our sun was still a collapsing cloud of gas and dust. It had been wandering through the galaxy for billions of years before Earth had cooled enough for the first oceans to form. While life was taking its tentative first steps in tidal pools on our young world, 3I Atlas was already a seasoned traveller, carrying within its frozen heart the chemical memory of stellar neighbourhoods that had long since dispersed. This temporal displacement creates a kind of cosmic archaeology. In studying 3I Atlas, we're not just examining a visitor from another place, we're examining a messenger from another time, a physical artifact from an epoch of galactic history, when the Milky Way itself was younger, more chaotic, perhaps more violent in its stellar birth and death cycles. The galaxy 7 billion years ago was a different place entirely. Star formation rates were higher, stellar collisions and supernovae were more frequent. The heavy elements that make planets like Earth possible were less abundant, still being forged in the nuclear furnaces of massive stars that had not yet lived long enough to explode and scatter their elemental gifts across space. In this earlier universe, the conditions under which 3I Atlas formed were likely unlike anything we see in our local stellar neighborhood today. Yet somehow, through all those eons of wandering, through gravitational encounters with countless stars, through exposure to the harsh radiation of interstellar space, through temperature variations that would cycle from near absolute zero to whatever warmth it might find during close stellar encounters, 3I Atlas has maintained its integrity. The ice hasn't all sublimated away. The rock hasn't been ground to dust by cosmic impacts. The organic compounds, if they exist, haven't been broken down by radiation. This preservation speaks to something remarkable about the nature of deep space itself. We tend to think of the void between stars as hostile, and in many ways it is. But it's also profoundly stable. Once an object achieves the kind of velocity that 3I Atlas possesses, once it escapes the gravitational wells of star systems and begins its journey through the galactic medium, it enters a realm where change happens slowly, where the conditions that would destroy it on a planetary surface simply don't exist. The temperature of deep space hovers around -270 degrees Celsius, just a few degrees above absolute zero. At these temperatures, chemical reactions essentially stop. Ice behaves more like rock. Organic molecules, if they exist, enter a kind of suspended animation. In effect, the extreme cold of interstellar space acts as a cosmic refrigerator, preserving samples from ancient stellar environments in a state of near-perfect stasis. But 3I Atlas hasn't been completely dormant during its journey. The very fact that we can see it, that it's producing the spectacular coma that makes it visible to our telescopes, tells us that it's awakening from its deep freeze as it approaches our sun. The solar radiation is beginning to warm its surface, causing volatile materials to sublimate and stream away from the nucleus in the characteristic tail structure that defines a comet. This awakening process is revealing chemical signatures that read like a fossil record from another world. The James Webb Space Telescope has detected an unusual abundance of carbon dioxide in the coma, far more than we typically see in comets from our own solar system. This high CO2 content suggests that 3I Atlas formed far from its parent star, in the cold outer reaches of its birth system, where carbon dioxide could condense into solid form. But the chemistry goes deeper than that. Observations have also revealed the presence of carbon monoxide, carbonyl sulfide, and even more exotic compounds, like cyanide and metallic nickel. Each of these substances tells a story about the conditions under which they formed, the temperatures and pressures and chemical environments that existed in 3I Atlas's ancient home. The abundance of carbon-bearing compounds is particularly intriguing because carbon chemistry is the foundation of life as we know it. While we certainly shouldn't leap to conclusions about biological processes, the rich organic chemistry of 3I Atlas does suggest that the building blocks of life might be more common throughout the galaxy than we previously imagined. If a 7 billion-year-old wanderer from the outer reaches of some long-dead star system can carry complex carbon compounds through interstellar space, then perhaps the chemical prerequisites for biology are being distributed throughout the galaxy on a scale we're only beginning to appreciate. The trajectory that brought 3I Atlas to us also tells a story of gravitational choreography played out across cosmic timescales. For an object to achieve the kind of velocity it possesses, for it to break free from its birth system and begin wandering between the stars, something dramatic must have happened. Perhaps a close encounter with a gas giant planet flung it outward like a gravitational slingshot. Perhaps the gravitational influence of a passing star disrupted the outer regions of its home system, sending clouds of comets and asteroids into the deep. Or perhaps something more catastrophic occurred. Stellar systems are not permanent fixtures. Stars evolve, expand, explode, collapse. Binary star systems can become unstable. Entire stellar neighborhoods can be disrupted by the gravitational influence of massive objects like black holes or neutron stars. The fact that 3I Atlas has been wandering for so long suggests that whatever sent it on its journey was powerful enough to impart tremendous velocity to break the gravitational bonds that once held it in orbit around its parent star. As it traveled through the galaxy, 3I Atlas would have experienced gravitational encounters with other stars, each one subtly altering its trajectory, gradually accumulating the incredible speed we observe today. These encounters would have been spaced out over millions or billions of years, each one imperceptible on human timescales, but collectively responsible for the hyperbolic trajectory that brings it through our solar system today. The path it has traced through space is essentially unreconstructible, like trying to determine where a leaf fell into a river by observing where it emerges at the mouth. The gravitational influences of countless stellar encounters have scrambled any clear signature of its origin point. We know it came from the general direction of Sagittarius, from somewhere in the thick disk of our galaxy. But beyond that, its birthplace remains one of the universe's well-kept secrets. This uncertainty adds to the mystique of 3I Atlas, but it also highlights something important about the nature of interstellar space. The galaxy is not a static structure. Stars move, systems evolve, neighborhoods change. Over the billions of years that 3I Atlas has been wandering, the stellar landscape it originally knew has been completely transformed. The star around which it once orbited might have long since evolved into a white dwarf or exploded as a supernova. Its sibling planets and asteroids might have been scattered to the cosmic winds or consumed by their dying sun. In a very real sense, 3I Atlas might be the only surviving witness to its original stellar system, the only remaining physical evidence that such a place ever existed. This makes it not just scientifically valuable, but almost poignant, a cosmic orphan, carrying the only remaining traces of a world that time has erased. The seasonal timing of its approach adds another layer to the story. 3I Atlas will reach its closest approach to our Sun in late October 2025, just as autumn settles over the northern hemisphere, as the days grow shorter and the nights longer. There's something fitting about this timing, as if the cosmos has arranged for this ancient visitor to arrive during the season when we're most inclined toward reflection, toward contemplating the deeper cycles that govern both earthly seasons and cosmic wanderings. But the window for observation is limited, and that limitation carries its own sense of urgency. Unlike the planets and moons and asteroids of our solar system, which we can study at leisure across multiple orbital cycles, 3I Atlas is a one-time opportunity. After it swings past the Sun and begins its journey back toward interstellar space, it will fade from view, disappearing into the cosmic background noise, perhaps never to return. This transient nature transforms every observation into something precious, every spectrum captured by our telescopes into an irreplaceable piece of evidence from the deep past. Astronomers around the world are coordinating their efforts, sharing telescope time, collaborating across international boundaries to squeeze every possible bit of information from this brief encounter. The data they're collecting isn't just about one object. It's about understanding the frequency and diversity of interstellar visitors, about building a census of what wanders between the stars, about beginning to map the invisible highways that connect stellar systems across the galaxy. Each new interstellar object we discover adds to this growing catalogue of cosmic travelers, slowly revealing patterns that hint at the larger dynamics governing our galactic neighborhood. And the patterns are already beginning to suggest something remarkable about the abundance of these wanderers. With 3 confirmed interstellar visitors detected in just 8 years, statistical models suggest that thousands of similar objects might be passing through our solar system at any given time, most too small or too distant to detect with current technology. We exist, it seems, in a river of interstellar debris, a constant flow of material being exchanged between stellar systems throughout the galaxy. This realization recasts our solar system not as an isolated island in space, but as a way station along ancient trade routes that have been carrying cargo between the stars since the galaxy was young. And 3I Atlas, with its extraordinary size and remarkable preservation, represents perhaps the most significant shipment to arrive at our cosmic port in recorded history. The chemical inventory that our telescopes are slowly compiling reads like a periodic table from another world. Beyond the carbon dioxide and water vapor that form the visible coma, deeper analysis reveals trace signatures that speak to processes we're only beginning to understand. The presence of metallic compounds, particularly nickel, suggests that 3 Atlas might contain materials that formed under pressures and temperatures quite different from those that shaped the rocky bodies of our own solar system. These metallic signatures could indicate that portions of the object originated closer to its parent star, in regions where rocky planets might have been forming, before some gravitational catastrophe scattered the building blocks of worlds into the cold outer reaches where comets typically form. In essence, 3I Atlas might be carrying within itself fragments of what could have been planets, worlds that never got the chance to coalesce, now preserved in frozen suspension for billions of years. The sulfur-bearing compounds detected in its spectrum add another layer of complexity to this chemical story. Sulfur chemistry often requires specific environmental conditions, particular combinations of temperature, pressure, and chemical activity that tell us about the dynamics of its formation environment. The presence of carbonyl sulfide, in particular, suggests chemical processes that might have occurred in the presence of both organic materials and volcanic or hydrothermal activity. This raises intriguing questions about the nature of the system where 3I Atlas formed. Was it a quiet, stable environment where materials slowly accumulated in the cold outer reaches? Or was it a more dynamic, possibly violent system where geological processes, stellar flares, or gravitational disruptions created the complex chemistry we're now observing? The answers remain locked within the ice and rock of the nucleus, waiting to be decoded as our instruments continue their careful analysis. The timing of these chemical revelations is particularly significant because it's synchronized with 3I Atlas's awakening. As it approaches the Sun, the increasing solar radiation is causing different materials to sublimate at different rates, essentially providing us with a layered chemical archaeology. The most volatile compounds, those that vaporize at the lowest temperatures, were the first to begin streaming away from the nucleus when 3I Atlas was still far from the Sun. As it draws closer, progressively more refractory materials begin to contribute to the coma, revealing deeper layers of the object's composition. This process is like watching an onion being peeled in slow motion, each layer revealing new chemical signatures from different epochs of the object's formation. The outermost materials might represent the final stages of accretion in its birth system, while deeper layers could preserve evidence of earlier, more primordial conditions. By carefully tracking how the chemical composition of the coma changes as 3I Atlas approaches perihelion, astronomers are essentially conducting a non-invasive biopsy of this ancient wanderer. But the chemistry is only part of the story. The physical structure of 3I Atlas, its shape and rotation and internal organization, provides clues about the forces that shaped it during its long journey through space. Unlike the planets and moons of our solar system, which have been shaped by billions of years of gravitational interaction and tidal forces within a stable stellar environment, 3I Atlas has been subjected to an entirely different set of influences. During its wandering through interstellar space, it would have experienced impacts from cosmic rays, high-energy particles traveling at near-light speed. These impacts, accumulated over billions of years, would have gradually altered the surface chemistry of the object, creating new compounds through radiation-induced chemical reactions. The outer layers of 3I Atlas might therefore represent a kind of cosmic weathering, a record of its exposure to the harsh radiation environments of deep space. Temperature cycling would have provided another source of structural stress. While the average temperature of interstellar space is close to absolute zero, 3I Atlas would have experienced periodic warming during gravitational encounters with other stars. These thermal cycles, repeated over cosmic timescales, could have caused expansion and contraction of different materials within the nucleus, potentially creating internal fractures or redistributing volatile materials. The gravitational encounters themselves would have subjected 3I Atlas to tidal forces, stretching and compressing the object as it passed through the gravitational fields of other stars. For a loosely bound collection of ice and rock, these forces could have been destructive, potentially breaking apart weaker structures. The fact that 3I Atlas has survived as a coherent object suggests either that it's more strongly bound internally than typical comets, or that it's been fortunate enough to avoid close encounters with massive stars during its journey. The rotation of 3I Atlas provides another window into its history and structure. As our telescopes track its movement across the sky, they're also measuring subtle variations in brightness that reveal how the object tumbles through space. This rotational signature tells us about the distribution of mass within the nucleus, about whether it's a single coherent body or perhaps a loosely bound collection of smaller pieces held together by gravity. Current observations suggest a rotation period of several hours, which is relatively slow compared to many solar system objects. This leisurely tumbling might indicate that 3I Atlas is indeed a substantial, well-consolidated object, rather than a fragile rubble pile. It could also suggest that any close gravitational encounters during its journey were gentle enough not to spin it up to higher rotation rates. The axis of rotation, its orientation relative to the object's trajectory through our solar system, provides additional clues about its dynamical history. If 3I Atlas were simply a chunk of debris blasted out of its birth system by a single, catastrophic event, we might expect its rotation axis to be aligned with its trajectory in predictable ways. But if it has experienced multiple gravitational encounters during its journey, each one subtly altering both its path and its spin, the relationship between rotation and motion becomes more complex. These rotational characteristics also affect how we observe the chemical composition of the coma. As different areas of the nucleus are exposed to solar radiation, they contribute different chemical signatures to the surrounding atmosphere. By correlating changes in the spectrum with the rotational phase, astronomers can begin to map the chemical heterogeneity across the surface of 3I Atlas, essentially creating a crude chemical map of an object that's too distant to image directly. The gravitational influence of 3I Atlas on its surroundings, while minimal compared to planets or even large asteroids, still provides measurable effects that help constrain its mass and density. As it passes near other objects in our solar system, particularly during its close approach to Mars in October, the subtle gravitational perturbations it creates can be detected by careful analysis of spacecraft trajectories and planetary motion. These measurements are crucial because they allow us to move beyond surface observations and begin to understand the internal structure of the object. Is 3I Atlas a solid rocky body like an asteroid? Is it a loosely packed collection of ice and dust like many comets? Or is it something intermediate, perhaps a differentiated object with a rocky core surrounded by icy material? The density calculations emerging from these gravitational studies suggest something intriguing. Initial estimates place 3I Atlas at a density lower than solid rock but higher than pure ice, consistent with a mixed composition of rocky and icy materials. This is not unusual for comets, but the specific ratio of rock to ice provides clues about the temperature and chemical conditions in the outer regions of its birth system. More intriguingly, the density estimates also help us understand the porosity of the object. Many comets in our solar system are surprisingly fluffy, with internal structures more like sponges than solid rocks. This porosity affects how heat conducts through the nucleus, how gases escape during outgassing, and how the object responds to external forces. If 3I Atlas proves to be highly porous, it would suggest that it formed through gentle accretion processes, with dust and ice particles sticking together under minimal gravitational compression. The magnetic properties of 3I Atlas, while more difficult to measure at such distances, might also hold clues about its composition and history. Some meteorites and asteroids carry magnetic signatures that record the magnetic fields present when they formed. If 3I Atlas possesses similar magnetic memories, they could provide direct evidence of the magnetic environment around its parent star, offering a unique window into stellar magnetic field evolution over billion-year timescales. As our observational campaign continues, each new measurement adds another piece to this vast cosmic puzzle. The infrared signatures tell us about temperature distribution across the nucleus. The ultraviolet observations reveal the behavior of the most energetic chemical processes in the coma. Radio telescopes search for emission from complex organic molecules that might be sublimating from the nucleus. But perhaps most remarkably, this observational symphony is playing out in real time. Unlike the study of distant galaxies or ancient supernova, where we observe events that occurred millions or billions of years ago, 3I Atlas is here, now, close enough that the light from our telescopes reaches it in minutes rather than years. The chemical processes we're observing in its coma are happening as we watch. The sublimation and ionization and molecular formation occurring on timescales we can follow from day to day. This immediacy creates an almost intimate connection with this ancient wanderer. Every night that skies are clear, telescopes around the world turn toward the constellation where 3I Atlas currently resides, gathering photons that left its surface just minutes before. In a very real sense, we're in communication with this 7 billion-year-old messenger, reading the chemical signals it's broadcasting as it awakens from its long sleep in the cold between stars. The data streams flowing back from our telescopes are being analysed in real time by teams of scientists working around the clock. Spectra are compared, chemical models are updated, theoretical predictions are tested against new observations. The scientific process, usually measured in months or years from observation to publication, has been compressed into days or weeks as the astronomical community recognises the unique nature of this opportunity. International collaborations have formed spontaneously, with observatories sharing telescope time and data in ways that transcend normal institutional boundaries. The Hubble Space Telescope, the James Webb Space Telescope, ground-based observatories in Chile and Hawaii, radio telescopes in Australia and Europe, all coordinating their observations to build the most complete picture possible of this cosmic visitor. The urgency is justified by the limited time window. As 3I Atlas approaches its closest point to the Sun, it will become increasingly difficult to observe from Earth-based telescopes due to the Sun's glare. The most active phase of its outgassing, when the most interesting chemical processes are likely to occur, will happen when it's nearly invisible to us. We have only a few months to gather decades worth of data about interstellar chemistry and physics. But the legacy of this observation campaign will extend far beyond the specific measurements of 3I Atlas. The techniques being developed, the international collaborations being forged, the theoretical models being tested, all of this infrastructure will be ready when the next interstellar visitor arrives. And statistical models based on the discovery rates of these objects suggest that we won't have to wait long. The Vera Rubin Observatory, which serendipitously captured some of the first detailed images of 3I Atlas, is expected to revolutionize our ability to detect and study interstellar objects. When it begins its full survey operations, it should discover 1 or 2 new interstellar visitors every year, transforming these rare cosmic encounters into a regular opportunity for scientific investigation. This prospect opens up the possibility of comparative interstellar astronomy, the study of how different star systems produce different types of wandering objects. Just as the study of exoplanets has revealed the incredible diversity of planetary systems throughout the galaxy, a catalogue of interstellar visitors could reveal the diversity of stellar system evolution, the different ways that stars and planets and smaller bodies interact and influence each other's development. Each new interstellar object will add to our understanding of galactic chemical evolution, the slow process by which heavy elements created in stellar cores are distributed throughout the galaxy and incorporated into new generations of stars and planets. 3I Atlas, with its unusual chemical composition and ancient age, provides a baseline measurement of these processes from an epoch when the galaxy was significantly younger and chemically different. The story of 3I Atlas is still being written, still being decoded from the faint signals reaching our telescopes, but already it has transformed our understanding of the space between stars, revealing it not as empty void, but as a medium rich with wandering worlds, each one carrying chemical messages from distant places and ancient times. As we peer deeper into the implications of 3I Atlas and its extraordinary journey, we begin to encounter questions that stretch beyond the purely scientific and into realms that touch the very foundations of how we understand our place in the cosmic order. This ancient wanderer, with its billion-year odyssey through the galactic dark, carries within its frozen heart not just chemical signatures and physical properties, but something more profound, a kind of existential weight that settles slowly into consciousness like sediment in still water. Consider what it means that objects of this magnitude can survive journeys between star systems. We're not talking about microscopic grains of dust or simple molecules that might drift on stellar winds. We're contemplating mountain-sized pieces of worlds, complex assemblages of ice and rock and organic chemistry that maintain their integrity across distances so vast that light itself takes years to traverse them. This preservation suggests something fundamental about the architecture of space, about the hidden durability that exists in the apparent emptiness between stars. The implications ripple outward in ways that are both humbling and strangely comforting. If 3I Atlas can carry the chemical memory of its birthplace across such immense spans of time and distance, then the universe is far more connected than our earthbound perspectives might suggest. The boundaries between stellar systems, which seem so absolute from our vantage point on this small world orbiting an ordinary star, are actually permeable. Material flows between them, carrying information, carrying history, carrying the building blocks of worlds that might never form, but whose potential remains suspended in the cosmic medium. This connectivity operates on timescales that dwarf human experience, yet it suggests patterns of exchange and communication that have been ongoing since the galaxy was young. Every star system contributes to this vast circulation, launching its own fleet of wanderers into the deep, while simultaneously receiving visitors from distant neighborhoods. Over billions of years, this process has mixed and remixed the raw materials of world building, distributing the chemical innovations of stellar evolution throughout the galactic disk. The age of 3I Atlas places it within a particularly significant epoch of galactic history. 7 billion years ago, the Milky Way was in its middle age, old enough to have synthesized significant quantities of heavy elements through successive generations of stellar death and rebirth, but young enough that star formation rates were still elevated compared to today. The metallicity of the galaxy, the abundance of elements heavier than hydrogen and helium, was lower then, which means that the planets and smaller bodies forming in that era would have had access to different chemical palettes than those available today. This temporal displacement makes 3I Atlas a kind of time capsule, preserving samples of matter that formed under galactic conditions that no longer exist. The ratios of different elements, the specific isotopic signatures, the complex organic molecules that our instruments are detecting, all of these represent snapshots of stellar nucleosynthesis and planetary formation processes from an era when the universe itself was significantly younger and more dynamic. The chemical richness revealed by spectroscopic analysis continues to surprise researchers with its complexity and unexpected abundance of certain compounds. The high carbon dioxide to water ratio, initially puzzling, now appears to tell a story about formation in the outer reaches of a protoplanetary disk where temperatures were low enough for CO2 to condense directly from the gas phase. But the presence of more complex carbon-bearing molecules suggests that this wasn't a simple, quiet process of accretion in the cold outer darkness. Instead, the chemistry points toward a more dynamic environment, possibly one where the young star was more active, producing bursts of radiation that drove complex chemical reactions in the surrounding disk. Or perhaps the disk itself experienced periods of instability, heating events that partially melted and reformed icy materials, creating the chemically heterogeneous mixture we're now observing as these ancient ices sublimate in the warmth of our sun. The metallic components detected in the spectrum add another layer of complexity to this formation story. Nickel and other heavy elements typically require high temperature processes to become incorporated into cometary nuclei. Their presence suggests that 3I Atlas might contain materials that formed much closer to its parent star, in regions where rocky planets typically accrete before being somehow transported to the outer reaches of the system where the icy components accumulated. This mixing of materials from different regions of a protoplanetary disk is not uncommon in our own solar system, where meteorites reveal similar chemical heterogeneity. But the specific signatures observed in 3I Atlas suggest processes that operated under different conditions, possibly in a system with a different stellar mass, a different disk structure, or a different evolutionary timeline than the one that produced our familiar planetary neighborhood. The gravitational dynamics that eventually launched 3I Atlas on its interstellar journey represent another chapter in this ancient story. The velocities required to escape a star system entirely are substantial, typically requiring close encounters with massive planets or even other stars. The fact that 3I Atlas achieved such high speeds while maintaining its structural integrity suggests that whatever process ejected, it was both powerful and relatively gentle, imparting enormous kinetic energy without completely disrupting the fragile ice and rock matrix. Computer simulations of planetary system evolution show that such ejections are most common during the early phases of system formation, when massive planets are still migrating through their orbits and gravitational interactions are frequent and chaotic. This timing aligns well with the estimated age of 3I Atlas, suggesting that it was launched on its interstellar journey during the youth of its parent system, possibly during the same kind of gravitational upheaval that scattered objects throughout the outer reaches of our own solar system billions of years ago. The subsequent journey through interstellar space would have been largely uneventful by human standards, but profoundly transformative in subtle ways. The cosmic ray environment, the occasional gravitational perturbations from passing stars, the slow accumulation of interstellar dust and gas, all of these factors would have gradually modified the object's surface chemistry and possibly its internal structure. Cosmic rays, high-energy particles accelerated by supernova shockwaves and other violent astrophysical processes would have been constantly bombarding 3I Atlas throughout its journey. These impacts, while individually microscopic, would have accumulated over billions of years to create an altered surface layer where radiation-induced chemistry produced compounds that might not have existed in the original material. Some of the complex organic molecules we're detecting might be products of this billion-year cosmic ray processing, making them signatures not just of the object's birth system, but of its long journey through the galactic medium. The gravitational encounters with other stars during its wandering would have been infrequent but significant. Statistical models suggest that an object like 3I Atlas might experience close stellar encounters every few million years, each one subtly altering its trajectory and potentially subjecting it to tidal forces and heating. These encounters would have been too brief and distant to significantly warm the nucleus, but they might have contributed to the complex tumbling motion we observe today, each gravitational interaction adding its own contribution to the object's rotational state. The interstellar medium itself, while extremely tenuous by terrestrial standards, would have provided a constant, gentle pressure on 3I Atlas throughout its journey. At the speeds it achieved, collisions with interstellar gas and dust grains would have been frequent, gradually eroding the leading surface and possibly creating the slight asymmetries that affect how we observe its outgassing behavior today. This constant interaction with the galactic environment means that 3I Atlas carries within itself not just the chemical signature of its birth system, but also a record of the interstellar conditions it has encountered during its long journey. The surface layers represent a kind of galactic sediment, accumulated grain by grain over cosmic time, preserving information about the density, composition, and chemical evolution of the interstellar medium itself. The magnetic environment of the galaxy would have provided another source of subtle influence during the journey. The galactic magnetic field, while weak, extends throughout the disk of the Milky Way and could have affected the motion of any charged particles associated with 3I Atlas. If the object carries any remnant magnetization from its formation era, this could provide a record of magnetic field evolution over billion-year timescales, offering insights into the large-scale magnetic structure of the galaxy and how it has changed as the Milky Way has evolved. The approach of 3I Atlas toward our solar system marks the end of this billion-year journey through interstellar space and the beginning of a new phase of activity and revelation. As it enters the realm of significant solar heating, the frozen materials that have remained dormant for cosmic ages begin to stir and sublimate, creating the spectacular coma that makes the object visible to our instruments. This awakening process is not uniform across the nucleus. Different materials sublimate at different temperatures, creating a layered revelation as 3I Atlas draws closer to the Sun. The most volatile compounds, those that can sublimate even in the weak heating of the outer solar system, were the first to contribute to the developing coma. As the object continues inward, progressively less volatile materials begin to participate in the outgassing, revealing deeper layers of the ancient chemistry. The rate at which this process unfolds depends not just on solar heating, but also on the internal structure and thermal properties of the nucleus. If 3I Atlas is a loosely consolidated rubble pile with high porosity, heat will penetrate slowly into the interior, creating a gentle, sustained outgassing that could continue for months. If it's a more consolidated object with lower porosity, the sublimation might be more intense but confined to a thinner surface layer. Current observations suggest something intermediate, with outgassing rates that are substantial but not overwhelming, consistent with a nucleus that has some internal structure but also significant porosity. This interpretation aligns with formation models that envision cometary nuclei as gentle accumulations of ice and dust that never experience the high pressures and temperatures that would compact them into solid rock. The chemical evolution of the coma, as 3I Atlas approaches perihelion, provides a real-time laboratory for studying sublimation processes under conditions that don't exist anywhere in our solar system. The combination of ancient chemistry, billion-year preservation, and exotic formation conditions creates outgassing behavior that differs subtly but measurably from that of familiar comets. The unusually high carbon dioxide content, for instance, affects how heat is distributed through the nucleus and how efficiently gas can escape from the interior. Carbon dioxide sublimation is more sensitive to temperature changes than water sublimation, which means that small variations in solar heating can produce large changes in outgassing rate. This sensitivity makes 3I Atlas a particularly responsive subject for studying the relationship between solar energy input and cometary activity. The presence of complex organic molecules in the coma adds another dimension to these studies. These compounds, some of which might be products of billion-year cosmic ray processing, sublimate at different rates and undergo different chemical reactions in the solar wind environment. Tracking how their abundance and distribution change as the coma evolves provides insights into both the original chemistry of the nucleus and the processes that have modified it during its long journey. The dust component of the coma, while less chemically informative than the gas, provides crucial information about the physical structure and composition of the nucleus. The size distribution of dust grains, their composition, and their ejection velocities all depend on the internal properties of the object and the mechanisms by which material is liberated from the surface. Initial observations suggest that 3I Atlas is producing dust at rates consistent with typical cometary behavior, but with some subtle differences in grain size distribution that might reflect the unusual formation conditions or the effects of long-term cosmic ray exposure. The dust grains themselves, when captured and analysed by future missions, could provide direct samples of 7 billion-year-old stellar system material, offering unprecedented insights into planetary formation processes in the early galaxy. The interaction between the outgassing material and the solar wind creates additional opportunities for study. As the charged particles of the solar wind encounter the neutral gas and dust of the coma, they drive chemical reactions and ionization processes that produce emission lines observable from Earth. The specific wavelengths and intensities of these emissions depend on the detailed chemistry of the coma and provide another window into the exotic composition of this ancient visitor. The magnetic properties of the solar wind also interact with any intrinsic magnetic fields that 3I Atlas might possess, potentially creating detectable signatures of the object's internal magnetic structure. While such measurements are at the limit of current instrumental capabilities, they represent a unique opportunity to study magnetic field evolution over billion-year timescales. As 3I Atlas continues its approach toward perihelion, the intensity of these interactions will increase dramatically. The solar wind becomes denser and more energetic closer to the Sun, while the outgassing from the nucleus increases exponentially with temperature. The result will be a crescendo of activity that should reveal the most deeply buried chemistry and provide the clearest signals for remote sensing instruments. But this intensification comes with observational challenges. As 3I Atlas draws closer to the Sun, it becomes increasingly difficult to observe from Earth due to the Sun's overwhelming brightness. The most active phase of its evolution, when the most interesting processes are likely to occur, will happen when the object is nearly invisible to ground-based telescopes. And so we reach the end of our quiet journey with this ancient wanderer, this 7 billion-year-old messenger from stellar neighbourhoods that existed when our galaxy was young. 3I Atlas continues its passage through our solar system, carrying with it secrets from a time before Earth's oceans formed, before life took its first tentative steps in primordial tidal pools. Its unimaginable size, its extraordinary preservation, its rich chemistry all speak to connections that span the galaxy, to highways between stars that have been carrying cargo since the universe was in its youth. As it fades from our telescopes and returns to the endless dark between worlds, 3I Atlas leaves us with a profound realization that we are not alone, not isolated, but part of an ancient conversation written in ice and rock and starlight. Sleep well, knowing that even now, other messengers are traveling toward us through the cosmic deep, carrying stories we have